Exercise number 18 presents a double integral and describes a region D. It asks us to express D as a region of type 1 and also as a region of type 2, then evaluate the double integral in two ways. So let's look at the region D being described here. D is the region enclosed by the curves y equals x squared and y equals 3x. Now it isn't strictly necessary to draw a graph, but I find one to be very helpful regardless. I tend to have a better time conceptualizing these things geometrically and dealing with them that way. So let's kind of sketch this out here. We have y equals x squared is going to be some sort of parabola, which I'm going to draw very poorly. And we have y equals 3x, which is a line cutting through the origin at some little slanty bit there. And based on this intersection here, thinking about how this would go, if we had slope of 1, we'd have the 1, 1. With the 3x, if we think about that, at 3, we can get 9. Of course, if you're a little bit uncertain where that's going to be, keep in mind we will often need to find intersection points, and these can easily be done algebraically, right? If y equals x squared and y equals 3x, we have x squared equals 3x. And if you treat that as a polynomial equation, do this, x squared minus 3x equals 0, x times x minus 3 equals 0, so that means that x would be 0, where we know that there's an intersection at the origin, or 3. And if x equals 3, y equals 9, so you can find your point 3, 9 as the other point of intersection. So depending on what you're doing, you could find that very helpful. This is the curve y equals x squared, and this line is y equals 3x. And D is the region enclosed between these. Make that a little bit better there. And we've got that bit in there is the region D. And we have this double integral over this region D of x times y dA. We're asked to express D as a region of type 1 and also as a region of type 2. We don't actually care, the textbook might, but we teaching this class don't actually care if you know which one is type 1 and which one is type 2. The point is that that refers to the two different ways that we can set up this double integral. So let's kind of look at that. We have this double integral over D of xy dA. And one way to set this up, the way that I usually find to be easiest, we'll make this an iterated integral here. And we have our xy. And I usually find it easiest if it's nice and easy to do so, to think of the integral with respect to x on the outside. So we would have dy dx. The outermost integral then, if we go from the outside in, we could say, all right, well, what are the bounds on this thing? We have x ranging between 0 and 3. So we have the integral from 0 to 3. And then for any particular value of x, choose any random point inside of here. You can ask yourself, okay, well then what are the bounds on y? Well, the lowest point on y is on this curve, and then as we go up, the maximum value of y is on that line, which means the lower bound here is x squared, and the upper bound is 3x. And we have just set up this integral. Another way to think about it is from the inside out. You could start by saying, okay, for random value of x, what are the bounds on y, and set that up internally, and then think about, okay, now that'll take care of this, that'll project this shape down onto the x-axis. What are we left with? That's 0 to 3, so you could fill in the 0 to 3 last if you wanted. Of course, it doesn't matter which order you do these things in. Now I'm relying heavily on the picture here. We could, of course, do this algebraically as well, by equating the equations, as we did here. We can solve and find that we have x equals 0 and x equals 3. And that suggests since these are the only 2 points of intersection, and we need a region that is enclosed by those curves, that suggests that 0 would have to be less than or equal to x, which is less than or equal to 3. In other words, x would have to be between 0 and 3, right? And then you can say, all right, well, if x is between 0 and 3, how do these quantities relate? And consider that you could pick a test point. Suppose x is 1. 1 squared is 1. 3 times 1 is 3. So you have that x squared is less than 3x. And that means that the y, which would have to be between those, the x squared would be below the 3x. The x squared is the lower bound. The 3x is the upper bound. So you could figure out which order those go in. So you don't actually need a picture. If you prefer to do this algebraically and using some inequalities, you can certainly do that. That works out just fine. Now we were asked to set this up both ways and also to evaluate it both ways. I don't want to go through the full evaluation, but it is important to look at how we would set this up the other way. So I'll go ahead and write this for a moment. The other order of setup would have the dx on the inside and dy on the outside. And now we can say, all right, well, y ranges from 0 to 9. Then what does x do? Well, for any particular value of y that you choose, the lower bound on x is the line, the upper bound on x is the curve. But we need to describe x in terms of y. So we would say that this equation here implies that x is equal to y over 3. Note that this is the double arrow implies. Some of you like to use single arrows for that, but we use single arrows for limits and convergence and whatnot, so let's not do that here. And if y equals x squared, that means that x is one of the square roots of y. Which one? Well, we look at this and figure out whether we have positive or negative values. We're looking at positive values of x here, so that means we need the principal square root of y. The lower bound on x, which is actually the left bound in this case, but if you find it helpful, you can kind of tilt your head to the right so that you're looking kind of up, down. But the lower bound in the numerical sense, the least value of x we have is on the line, y over 3. So our lower bound there is y over 3. This is on dx, remember. X starting at y over 3 and going up to x equals the square root of y. It's the upper bound on that. So this would be the alternate way to set that up. One of these is type 1, the other is type 2. I think I have them in this order, type 1 and type 2. I'm not even certain myself. I haven't actually checked that in a while. If WebAssign asks you anything, just check the textbook to see which one's which. But we don't really care about the numbers. The important part is being able to set these up appropriately for the order of integration. Whichever order of integration you use determines how your bounds are written. Notice on both of these that the outer integral has constants in the bounds, and the inner integral can potentially have bounds that depend on the outer variable. They could be constant as well, but this integral is inside an integral dx, so we can have x in the bounds. We wouldn't be able to have y here because the integral is dy, and that's a conflict of notation. Similarly over here, the outer integral is dy. Being an outer integral, it needs constants in its bounds. The inner integral is dx. Its bounds cannot be in terms of x, but we can specify x in terms of y, since that's an outer integral. This inner integral is a partial integral dx. As far as it's concerned, y is a constant. So you can have y there, and that's not a problem. So these are two different ways of setting this thing up. We're asked to evaluate both. I'll just run through one of them. The simpler one, I think, is this one here, the first one. So I'm going to draw a little squiggly line to set that off so that this line of work that I have here is not going to be messed up by that. And we'll just continue this little equals the integral from 0 to 3. We have x, y, dy. Integrating dy, we see that that is 1/2 x, y squared. And that is from the lower bound of y equals x squared to the upper bound of y equals 3x. and that's all dx. So I've evaluated the inner integral and just copied the remaining bits from the outer integral. Let's go ahead and bring the 1/2 out front. I don't think it's going to do any good to leave that inside of there. At the upper end, we have 3x going in for y. So we have the square of 3x. That's a 9x squared. So we have 9x cubed after we multiply by the x here. Minus, plugging in x squared for y, that gives us an x to the 4th. So that looks like x to the 5th. We need to multiply this by dx, so that means we need to insert some grouping symbols here. Because, of course, we want dx to be multiplied by the whole thing, not just the x to the 5th. So these grouping symbols are important. Do not fall into the trap that some students have developed of thinking of the integral and the dx as if they were themselves grouping symbols. They're not. The integral works like a sum, and the dx is a quantity being multiplied by the integrand. So if you have more than one term in the integrand, you need to group those together. That'll be increasingly important in chapter 16 when we work with certain forms of line integrals and we have multiple bits all included under the same integral. So make sure you have appropriate grouping symbols where necessary. Anyhow, at this point, we just have this as a Calc 1 integral. I don't think there should be anything too fancy here. Let's just sort of see what happens. Looks like we get 9/4 x to the 4th minus 1/6 x to the 6th, evaluated from 0 to 3. Up here, we needed to write y equals because we have both x and y. Down here, there's only one variable left. You could write x equals 0 to x equals 3. It's not really necessary since there's only one variable that we could possibly be substituting in for. And since I'm trying to do this mentally, or at least with as little writing as possible and no calculator, I need to be a little clever here. 9 is 3 squared, and 3 to the 4th there, so that gives us 3 to the 6th over 4, minus 3 to the 6th over 6, minus some zeros. So actually what I should probably do is write this as we have 1/2 times 3 to the 6th times 1/4 minus 1/6. So what'll this be? We have a common factor of 12. So that'll be 3/12 minus 2/12 leads 1/12. If I am doing that correctly, I'll check the answer at the end to make sure that it's working out well. 12 has a factor of 3 in it. So I think we get 3 to the 5th over, canceling out that 3 leaves a 4, so we have an 8. I don't know 3 to the 5th off the top of my head, but 3 to the 4th, of course, is 81. So that's 3 squared squared. And 3 times 8 gives us 24, and times 1 is 3, so it looks like 243/8, which is a slightly weird fraction, but let me check my notes here, and yes, that is indeed the correct answer that we end up with at the end. 243/8 is the value of that double integral. There are a couple of ways of interpreting that, of course. Right now, we're mainly thinking of this, the integrand, the function xy, as being a z value. So you can imagine this describing a surface that sits above this sliver here. And then we would be computing the volume under that surface, or the volume of the solid that's below that surface and above this region D. But, you know, we'll see more in later sections, but we might have seen a little bit already. We have other interpretations. XY could represent, you know, a mass density function or a charge density function or a probability distribution function or all kinds of different things. But basically, there we go. You might find it a useful exercise to come back to this alternate version. The other order of integration should evaluate to the exact same answer. So you might want to try working through that and confirming for yourself that that works out correctly. If you're in a situation where you don't just have an answer in the back of the book to look up, it's nice to have both ways to work these out so you can try it both ways. You can set up the integral both ways, evaluate it, and make sure you get the same answer in the end. There are certain kinds of errors that won't catch, right? Like if you set this up incorrectly, if you find an incorrect intersection point or something else, then, well, you're kind of out of luck. But many of the computational errors that you might make along the way in evaluating one of the integrals, it's probably unlikely that you would make an equivalent error in the other one that would give you the exact same result. So working through both of those can be a nice way of checking your own work.